Hello, I'm back with the second half of the 2017 Paper 2 TMUA. So 10 questions, see how these pan out. Question 11, function f of x is increasing, f of 0 is 0. Positive constants a and b, a is less than b. Area of the region enclosed by the curve y equals f of x, the x-axis and the two vertical lines, right, is denoted by r. So we've got some function f of x. So f of x is 0 and it's increasing. F of 0, I mean, is 0 and it's increasing. So it's going through the origin, it's going up in some way. We've got two vertical lines and then we're calling this thing r. So that's r. A is less than b, so that's a, that one's b. Okay, function g of x is defined by g of x is f of x plus 2f of b. So f of b is this. So we're going up by a certain amount. Two lots of that all the way along. Okay, which of the following is an expression for the area enclosed by g of x, the x-axis, and those two lines? Right, so we've shifted everything up. We've got some area r that we've then moved up by two lots of f of b. Okay, so that's still going to be r. This is between a and b, so we're going to have b minus a times 2f of b plus r. Which is that the first one? No, it's the second one, isn't it? B. That looks like B. Yeah, B. Okay, interesting question. Question 12. Diagram shows the graphs of y's sine 2x and cos 2x between minus pi by 2 and pi by 2. Okay, fair enough. Which of the following is not true? So in those ranges, they're comparing cos 2x, sine 2x, and tan x. Okay, right, let's draw a tan x on then. So that's just tan x, not tan 2x. So it's going to go through, well, here, and it will go through, well, it's going up to an asymptote up here. So it's going to be doing something like this and something like that. And now we want to see which one of the following is not true. So cos 2x, let's write which one's which is. So we've got cos, sine, and then tan is the blue one, obviously. So cos less than sine less than tan. Yeah, we can certainly do that. Like if we go here, cos is less than sine is less than tan. So that one's fine. Then cos less than tan less than sine. Cos less than tan. Yeah, I mean, that would work like if we were here. Cos is less than tan, which is less than sine. So that's fine. Sine is less than cos is less than tan. Sine is less than cos is less than tan. So for sine is less than cos, we've got this, all of this bit, and less than tan. Sine is less than, that's not going to work, is it? Because if I've got, well, for cos to be less than tan, it's got to be that way onwards. It's got to be there onwards. But for sine to be less than cos, it's got to be from there that way, well, up to here. So that doesn't fit. That really doesn't fit. So just check the others. Sine, tan, cos. So sine is the smallest, then tan, then cos. That would work for, say, here. Then tan, sine, cos. That would work for, say, here. And then tan, cos, sine. Tan, cos, sine, which would work, say, over here. Right, so yeah, it's definitely going to be C. Now, another interesting question. All right, 13. The positive real numbers A times 10 to the minus 3, B times 10 to the minus 2, and C times 10 to the minus 1 are each in standard form. Add the first two, get the third one. Which of the following statements must be true? Right. So we got 10 to the minus 3, 10 to the minus 2, and they've got to add up the sum, which is getting to 10 to minus 1. So we're having to carry, yeah, so standard form. So that means that our A, our B, and our C, they're going to be less than 10, but they're going to be greater than or equal to 1. So otherwise it's not standard form. So what does that mean? That's going to mean that, so A, we need to be carrying something into the B column. Let's put it into columns. So we got A, so it's going to be 0, 0, 0, and then A is going to start. So that's going to be a whole sequence of digits. So let's call it A1, A2, A3 onwards. Then we'd have a 0.0, and then a B1, B2, B3, and onwards. And then they're going to add up to give a 0, C1, C2, C3, and onwards. So we need to have a, we can never carry more than a 1, can we? Because we can't add up an A and a B digit. There's only 2 digits, so we can't carry a 2. So we need to have a 1 there to add to the B to get a 1. So C1 is going to be equal to 1 and B1 is going to be equal to 9. So we know that for sure. So, but that isn't the whole of B, or is it fitting with? I'm just looking at this B being greater than 9. I mean, it's going to have to be, isn't it? Because we need to carry something over from the previous column. So if B2 were a 0, we wouldn't be able to carry anything over even if A1 was 9. So B's definitely going to be greater than 9. Is A going to be greater than 9? Well, no, because we just have to have that A1 plus B2 is 10 or more. But it doesn't matter how we actually split those things out. So let's ignore 1. And then A less than C. A doesn't have to be less than C for the same reason that A doesn't have to be greater than 9. Because we could have 5 and 5 here for A1 and B2. So let's ditch that one. And B is less than C. Well, C starting with 1 and B starting with 9. So that's not going to work either. So it's going to be 2 only, which is B. Right, okay, that was a tough one, I think. 14. The diagram below shows the graph of y equals x squared minus 2bx plus c. The vertex of this graph is at the point P. Okay, which one of the following could be the graph of y equals x squared minus 2 capital B? Right, so they've increased the value of this thing. So what's going to happen on that? Well, B, whether lowercase or uppercase, that's the x coordinate of the minimum. You're just completing the square. So we'll move it to the right, but then we're going to have to subtract more, aren't we, once we complete the square, because we'll be taking off a capital B squared rather than a little b squared. So it's going to move right and down, which is F. Okay, so that was a really quick one. 15. The function f is defined on positive integers as follows, and then g as positive integers as follows. Okay, well, it's quite complicated. What's the value of f 1000 minus g 1000? Okay, right, these are clearly going to be looping if we have to go up to 1000, I would have thought. So f1 is 5. We've got f2 is, so if it's 5, fn is odd, we're going to get 16. Then we got even, so we're going to halve it to 8, halve it to 4, halve it to 2, halve it to 1, and then we're going to get 4. Right, so now we're looping 3, 4, 5, 6, 7, and we're doing this in, even the first bit's a block of 3. So it's blocks of 3 all the way along. So that'll take us up to 999, and then we do the first one of a block. So f of 1000 is going to be equal to 4. So for G, we've got G1 is 3, so G2 is going to be 8. Then we're going to go G3, 4, 2, 1. Okay. So what happens with 1? We're going to get 6. Then we're going to get 3. Oh my word, this is, we're back to the start. We are back to the start. So we're doing blocks of 6 on this then, by the look of it. I've definitely done that right. Yeah, that looks right. So we're doing blocks of 6. So that'll take us up to what, 996, and then we'll do the 9,789,000. So it'd be 2. So we're doing 4 minus 2 is 2, which is D. Okay. Consider the following statement. If f of x is an integer for every integer x, then f dash of x is an integer for every integer x. Okay. Which one of the following is a counterexample to that? So for A, we've got that. Yeah, but that doesn't work straight from the outset, does it? If you put 1 in, you're getting 3/4. So if f of x is an integer for every integer x, well, it's not, so it can't be a counterexample to it. Well, we've got the same for the second one, 3/2. I'm definitely reading this right. F of x is an integer for every integer x. Yeah, it seems to be. I mean, we are getting, what, 2 and 1 for the others, so these seem plausible at the bottom. If we put 0 in, we're still going to get the same. I don't really fancy putting 2s. Well, actually, if we put 2s in, they'll all be fine as well, because, yeah, we've got multiples of 2 and 4 and everything. So, yeah, I don't know. Let's look at these a bit closer then. F dash of x, so 4x cubed plus 3x squared plus 2x plus 1 all over 2. F dash of x, 4x cubed plus 6x squared plus 2x all over 4. Right, notably on this one, if we put 0 into C for f dash, then so f dash of 0 is equal to a half. So that would go against the second part if it, but how would we know? Because this one's going to work for D. If we put 0 in, we're fine. If we put 1 in, we're getting 12 over 4, which is fine. What if we put 3 in? That'd be what, 108, and then 54, and then 6, so 168, which also works. Right, maybe it is going to be C, but how do we know? And we got the counterexample in the second part, but how do we know that f of x is going to be an integer for every integer x for this? Factorise probably. So we want it to be even because we're dividing by 2. So I can say, okay, we've got x. I don't want to put that in brackets, but still. So x cubed plus x squared plus x plus 1. So I want to have x squared plus 1, x plus 1 to be even. So if x were even, then I'm going to get even times odd, which is even times odd, which is even. So that's fine. If x is odd, then I've got odd times even, which is odd times even, which is even. So yeah, this is always going to be even, and we're dividing by 2. And we've got the counterexample. Okay, so C. Right. That was another tough one. 17, right. A set of whole numbers is called stapled if and only if for every whole number A, which is in S, there exists a prime factor of A, which divides at least one other number in S. Wow, that's going to take some, I'm going to have to reread that a couple of times, I think. Let T be a set of whole numbers. Which of the following is true if and only if T is not stapled? Right, so we need to break this idea of stapled. Right, so let's just clarify this a bit. So we've got a whole it's a set of whole numbers. Right, so it's stapled, so we need every number. So that's one thing. And there needs to be a prime factor of that number, which goes, right, every number needs a prime factor that divides an other number. So we've got an every and 2 a's. Right, so we've got like a very strict condition here that every single number has to satisfy this, but it doesn't have to be all the prime factors, and it doesn't have to divide into all other numbers. Right, so what are our options? So we've got for every number in A, I mean, that's already going to fall down on these. How have they split these answers? They've got every number, or there exists a number. Yeah, so it's definitely going to be, because we only need one number that doesn't fit. We don't need every number to go wrong. So I can already cross out all of A to D. Right, so there exists a number A, which is in T, such there is no prime factor of A, which divides every other number in T. But we don't have to divide every other number, do we? Just have to go into another number. Is that right? There is no which divides every, yeah, so it's not going to be E, because that's just too strict again. So let's just sure I'm getting that right. So there is no prime factor of A, which is what we want. We want none of them, which divides every other number. That's just going too far. There exists a number a, yeah, no prime factor of a which divides at least one other number. That seems to be it to me. So we need a number, just any one of them, to break the every bit, and then no prime factor breaks the a bit in prime factors, and divides at least one other number. Yeah, that seems good. So what are the last two, just to make sure? Exists a number in a prime factor of a which does not divide any other number in t. Well, we can have that because we don't have to have all of the prime factors dividing into every other number. And as a prime factor of a which does not divide into at least, yeah, so again, that doesn't, these are too loose, the bottom two, and the first five are too tight. So yeah, it's going to be F. Yeah, I'm happy with that. Consider the following problem. Solve the inequality that where n is a positive integer, student produces the following argument. Oh, is this going to be where has it gone wrong? Which step, if any, in the argument is invalid? So we've got a quarter to the n being less than 1 over 32 to the power of 10. Well, it's clearly not true. So he's clearly messed it up somewhere, because if n is 1, I mean, it's not even close, is it? So it's definitely not a. So what is he doing then? So he's taking log base a half. Well, that's a big jump to come in. Is that okay? Can you do log base a half on that? Or does that flip sign? Does it flip sign? What happens with log base a half? So I've got, let's come back to it. I've got suspicions about that one. Then what's he done later then? So it's then bring down the powers. That's fine. That's not going to affect anything. Then divide by log base a half of a quarter. So he's divided by 2. So that's not a problem. Then replace the values. Oh, so he's put the 2 there, and that is 5. So that's fine. Oh, and he said it's 25, 50 over 2. So that's fine. And then said that n is less than 25 and it's greater than or equal to 1. And what did we say about n? N is a positive integer. So that's fine. So it's got to be this thing with a log base a half. So if we were going to draw this out, so log base a half, well, it's going to have to go through 1. But as we're getting larger and larger, so I'm doing log base a half of x equals y. So we've got a half to the y equals x. So as x gets really big, y is going to have to get big and negative. So it's going to have to go down here. And then as x gets small, y is going to have to get big and positive. So it's doing this. So what does this then mean for these things? I suppose it depends where we are, doesn't it? I mean, if we're doing logs of these things, so say we add, well, let's think if they were which way round they were. So say we add the small one, so we've got small less than big, and then we do log base a half of it. Yeah, it's going to flip it around, isn't it? It is going to flip it around, because now the small number is going to have a higher value. The smaller x we've got, the higher y. So when we do log base a half, it's going to flip the inequality around. So yeah, that's where it's gone wrong, step 1. So B. Okay. Question 19. Which of the following is a sufficient condition for the equation that where a is a constant to have exactly 1 real root? So positive cubic, 1 real root. So we either have to have the minimum below the x-axis, I mean the maximum below the x-axis, or the minimum above the x-axis. So what are we going to be doing with this? And so differentiate is going to be the thing, isn't it? So minus 6x. So that is going to be 3x and then x minus 2. So we've got a turning point at 0 and a turning point at 2. So we've got a max at x equals 0. And we've got a min at x equals 2. Okay, so when x is 0, we need this to be below the x-axis. So this means that a is going to have to be less than 0. And when x is 2, we're getting 8 minus 12 plus a, and that has to be greater than 0. So we've got that A has to be greater than 4. Is that right? Yeah. So where does that fit out of all of these? So we can't have A, can't have B, can't have C, can't have D. Okay, then we've got some of these. Mod A is greater than 4. Mod A is greater than 4. That is sufficient. That would work because it would give everything -4 downwards and 4 upwards. So that would work. This wouldn't work. That doesn't work. And that doesn't work. Right, so yeah, E. Right, that's good. 19. These are going all right, actually. I don't seem to be that much more difficult than the first half of the paper. But then I saw this in paper 1. There's not much variation in the difficulty of the question based on position in the paper. So, and this is the last one already. So I have forgotten my 5-character computer password, but I know that it consists of the letters A, B, C, D, E in some order. When I enter a potential password into the computer, it tells me exactly how many of the letters are in the correct position. When I enter A, B, C, D, it says none of them are correct. Same with that and that. So I've done A, B, C, D, E, C, D, B, E, A, D, B, C. Okay, so none of those are in the right place. Using the best strategy, how many further attempts must I make in order to guarantee that I can deduce the correct password? Right, so not how many to actually enter the right password, but to deduce it off the back of it. So what have we got in it? So that could be B or D. That could be C or E. This could be A or E. This could be A or C. And that could be B or D. Okay, so we've got 2 blocks then. We've got the B, D options for first and last. And then we've got the A, C and E bits in the middle. So say we put in B and D for first and last, and then went C. Well, if we had C second, we'd have to have A fourth, which means we have to have E in the middle. So if we put that in, what are we going to get as our return on this? We could get 0 again, because it could be, what's the other option we've got? We could have D and B, and then we've got 4 options then, haven't we? Because we could have D, C, E, A, B. We could have D, E, A, C, B, or we could have B, E, A, C, D. So we've got 4 options that we could have. So if we get 0, then we know it's going to be this one. If we get, say the B and D were right, so we had 2 of them, then we know we've got that one. So that's 0, that's 2. If we get 3 of them right, so the middle ones, then we know we're getting this one. And if we get 5 of them right, then we know it's this one. So we need to do 1 more, and then we're all right. We know what we're going to get. Okay, they went through a bit easier than I thought they were going to be. I mean, maybe I could have done all of this paper as one video. I mean, that last one was pretty straightforward. 19 was straightforward. I mean, 18 was maybe a little fiddly as to seeing what the problem was with log base a half, but in order, to actually see that was the invalid step wasn't that bad. The stapled took a bit of unraveling. Then 16 was fine. 15 was fine. 14 was really easy. 13 I think was the tough one. 12 was straightforward, and 11 was pretty straightforward. So I would say it was 13 and 17 were the nasty ones out of that block of 10. But all in all, I don't think paper 2 was actually any more difficult than paper 1. So, but I suppose it depends on your preferences on these things, doesn't it? But still, it's nice to have got through this first batch of TMUAs for finishing 2017. So I'll crack on with 2018 when I've got some time.